Hello developers, let's start developing. My name is Veko and today we're gonna solve the 12th task of the Advent of Code 2021. Let's take a look at what it is. With your submarines, subterranean, subsystems, subsiding, suboptimally. Okay, try saying that 5 times fast. The only way you're getting out of this cave anytime soon is by finding a path yourself. Yay! Pathfinding. Not just a path. The only way to know if you found the best path is to find all of them. Okay, so I'm already thinking that we're gonna need some depth first or breadth first search through some kind of grid. Fortunately, mostly working, so you build a rough map of the remaining caves. This is our input. Let's take a look. Aha. So I guess we're given a set of nodes and then we need to do something with them. This is a list of how all the caves are connected. Yep, these are the connections and the nodes are implicit. Basically, everything that is mentioned is a node. So we have start, start, A, B, C, D, and end. And I guess we need to go through A. Yep, okay, yep. Looks like this. You go to find a number of distinct paths that start at start and end at end. And don't visit small caves more than once. What is a small cave? These, I guess. Aha. There are two types of caves. Big caves written in uppercase and small caves written in lowercase like B. It would be a waste of time to visit any small cave more than once, but big caves are large enough that it might be worth visiting them multiple times. Okay, so anything like Dijkstra or something like that wouldn't work because, by definition, it uses a node when it visits it, and we want. So this means that start A, B, and no. I guess that when we got to end, we're done. But we can go start A, B, A, C, A, and. Aha. So we can go start A, B, A, C, A, and. Yep. There are 10 paths through this example cave system. Cave D is never visited. Yeah, if we get to cave D, we would have to return through cave B so that we can basically trim cave D. Here is a larger example. And this uses the trick that I already saw in the input, that the start node and the end node are not given as they should, but we might have other ways to do that. We have 19 paths, and this example has 226 paths. How many paths to this cave system? There visit small caves at most once. So yeah. Anyway, let's start with some input parsing. Let's take a look at these as well, so that we don't have any mixed smallish, largish. So they are multiple letters, but they are either all uppercase or all lowercase. So first off, what I'm gonna do in order to have my input taken, this will be an interface called input, and it will have a start, that's a string, and an end, that's a string. I would like this structure to be kind of better designed, but that will take some processing, and I don't want to be that in the input ingestion part because that will take some time, and to be honest, I want to count that time. In principle, I could do everything in the process input, but then even if my actual processing is very fast, I will say, yeah, it's very fast, but it takes 2 days to get it running. So I will leave any processing of the actual input, any transformation of the input for the part 1 code and not for the process input code. So the process input code will simply do, read the input lines, map the input, split it on a minus, and then map it. That's items, and then we need to return something that has start. No, we don't need to split anything. Items of 0 and end at items of 1, and we're just return the values. So we will not have an input array, we will have a number array, we will have an input array. Is this okay? We need it like this, so we added an extra array somewhere. Let's not that, so that we can take a look at the input that we got. Start A, start B, AC, AB, BD, A end, B end. Okay, we successfully ingested the input. So now what I want to do, I want to actually create some sort of graph or something like that that connected the matrix. So let's see what that should be. Let's model it. Caves. So the caves will have a list of nodes. Let's have that here. And what is a node? Well, the node has a type, and that can be start or end or big or small. And connections, which are other nodes. And we can say that caves is just an array of nodes. Let's try this on for size. Maybe we have a good structure, maybe we have an awful structure. But one thing that is okay, that all of these are reversible. If start connects to A, that means A connects to start. So what we can do is we can, for item of input, Okay, we have the caves. No, actually I want the caves to be something else. It's not gonna be an array of nodes, it's gonna be a map of nodes where key is a string, and the node will also have a name, which is a string. Yeah, I could, for example, model this a bit better, but I think it will be about the same, so that we can have formal start and end nodes and big and small nodes, but this will work just the same. So we have a key that is a string, and then we have a node. So now we can have var a const caves, that's an empty object. So if caves has the start, doesn't have a start item, first of all, let's get all the node names. We can map the input. We can just take these and have them flattened, and then we can, what was the structure that, yeah, new set from this, and we can do this to get that into an array. Yeah, this is a trick that we can basically use something to get the distinct values. We're putting them into a set, and a set by definition cannot have the same element multiple times, and then we're creating that into an array. So we have start A, B, C, D, and end. We're getting all the nodes. So let's, now if we have the node names, we can create all those nodes. So we can say caves of node name is a new. Let's have it. Should have a type, we should have a name, and it should have empty connections. Now we only need to determine the node type. So if node name is start, and that's a constant, then we can have something like type equals, yeah, that is a node type, equals small. But if node name is start, then it's, otherwise if it's end, type is end, otherwise the type is big, but this won't be like this. It will be if this equals node name dot to uppercase. Otherwise it's small. So we just can use the type. Let's see if we get the type correctly. So start is a start node, A is a big node, B is a small node, C is a small node, D is a small node, and E is an end node. Let's try to run this on our larger example, on our real example, to see if we are getting the correct values once more. Small node, big node, small node, big node, small node, end node, big node, small node, start node, small node, small node, small node, big node. Okay, looks like this part at least is working. So after we're done with this, we have our nodes created. So we need to process the links between the nodes, and for that I will just say get every links and do this. Push the other thing inside the connection. So let's see what we have now for our small example. Start has, let's just take the number of connections first. Start has 2 connections, okay. A has 4 connections, 1, 2, 3, 4. B has 4 connections as well. C has 1, D has 1, and End has 2. And you know what? The connections shouldn't be a node array, it should be a string array. We have the names are enough. So we don't need such a deeply linked thingy. Let's see if this works better. Yep. And since I'm sensing that we will have a lot of recursion, I'm gonna add a simple helper. That's just gonna do json.parse of json.stringify of input. Yeah, this is a quick and dirty JavaScript trick, or TypeScript trick actually in this type, since we are doing it in a type-safe way. When we are just taking an object, creating its string representation and creating it again as an object, and this effectively will do a deep copy, a full deep copy of the object. And if I had this recursive reference, because a node points to a list of nodes, this won't work. So that is one of the reasons that I changed it. So anyway, we have the caves. And we will have a list of pets, and then we will just need to return the length of pets. So what we will need to do, we will need to add one more method, and that will be get me all the pets for these caves using this start until this end, and that's all there is. Ooh, no, I want something else. I don't think that will work, because recursion usually takes a lot of thinking, and I, to be honest, don't want Copilot to do that thinking for me, because a simple, some kind of a simple off by one thing could have a disastrous result, so we won't have anything. But anyway, here we will just say paths are get paths for the caves starting from the start node. Actually, yeah, we can just use this. and this will return a string array. Return an empty array so that everybody is happy. So this will work and return a very successful 0 and a very incorrect 0. Yep. So we said give me the path for this set of case from the start to the end. So what I will do, I will just say, not that, give me start node is basically case of start. Start node connections. Those are the next ones. Okay. And in essence, one thing that I'm not sure of, and I'm actually sure of it right now, end and start and end are actually small caves, which means that once we visit them, we're done. Yeah, because otherwise here we could loop, have basically an infinite amount of values. Let's have it here because we can go start A end and then go to A and go to end and go to A and go to end, and that's kind of an infinite list. So we need to treat start and end as small nodes. Let's see if that actually makes sense, because we don't need the start and the end nodes. We just need to know that that's where we are starting, and we are giving that information basically here. What this means is that once we use any node that connects a cave with a small letter, a small cave with a large cave, this kind of disappears. So let's do this. So after the first move to A, this becomes this. And then we can move to C. But when we move to A, this disappears. So if we are moving toward the small cave, it doesn't disappear. But if we are moving toward the large from a small cave, so that's the rule. When we are moving from a small cave somewhere, that thing disappears. So we're moving to end, this doesn't disappear, but we get to end and we're finishing. Or we can go to B and this doesn't disappear, but then if we go back to A, this does disappear. And then we are only left to go to end. And on the other hand, if we start going from start to B, this disappears, and then from B we can go through A, this doesn't disappear, but and that disappears because we cannot go back. or if we're going to go to end and then this disappears and we are there. Yeah, makes sense. So we are getting all the connections from our start position. Is any of them the end one? Yep. So if next dot name, oh, this is a string. If next equals end, then we're done. That's the path that we will need to take. Oh, no. Basically start to end. If, and that's all we need to do. So we're just gonna need to do a continue. So here next is not the end, and we will need to get all the others. So let's see what kind of node this is. So if node is big, it doesn't matter whether we are going into a big node or into a small node. It matters whether we are moving from a start node or not. Yep. So what we want to do is to have our network of caves changed in such a way that it doesn't have that specific connection. Let's start with that. No. No. Let's do this here. That's a copy object of the caves. This is the next caves. So if we're coming from if the start node is small, that means that next caves we can remove the start node. That means that we don't have a start node. Because if we cannot go, yeah, we can totally remove it. Because we were at the start node, and when we move from a small node, that node is gone forever. So we are here, and this is our start node, new start node that we can move around from. Yep, kind of makes sense. And we can just But I now need to iterate over an object, and that's a foreign. I know it has all those things, and this is a node. Next node, that's next case of key dot connections. Yeah, we don't need to assign anything. Doesn't equal start. So we are removing every mention from start from the next case. Once, if we are getting to that. And we need to do that actually here. So that only happens if we are moving from a small node to a big node. And this is quite important if we are moving away next. Actually, we can take this in front of this, because if the start node is small, it disappears once we get going. If it's small, if it's large, then it just doesn't. So what happens next? We have our node, and we can say get me all the paths for the next caves when we're starting from the next and moving to the end. And then basically map that. Yeah, no. Yeah, actually. Because we will have an array list of paths. No, map is might be. Yeah, for each would be better. Those are the node paths, and then for each of node path of node paths, exactly, result dot push start, and push start at the beginning of each node path. And this could be right. I have no idea. That's the problem with recursion, that it is relatively simple, and if it works, it's great, but if it doesn't, there's quite a bit of debugging. Let's see. We can get 1 path, 10 paths, million paths, an error, or whatever. And we got an error that says we cannot read the start node connections of undefined. There should be a start node. One way to find out. Caves does have a property called start. Yep. And let's see. The start node is yes, that. And then we have the next. Oh, it blows up somewhere around in the recursion. That's okay. So the next caves also have a start property, and we have a small node, so we're gonna remove it. So next caves does not have a small property, but I know that A has a connection to start. Key is A, next caves of A, connections. Let's see, next caves of A, connections. and I'm a bit of an idiot. How do we stop this? Yeah, like this. Filter just filters, we need to actually assign it. We can do some kind of other removal, but let's keep it like this. Let's run this one more time to see if this makes sense. Just run it. We got a bunch of paths and it says we got 10 paths. Okay, and we wanted to get 10 paths. Let's have the slightly larger example. And let's remove the breakpoint. Now we got 19 paths. Okay, this even larger example. Let's take a look at the even larger example and see how many paths there are. $226 paths. Well, I'm quite confident that my recursion is actually recursing. So let's take the huge example and try to run it. And let's see if we get a billion paths. We've got 3,292 paths. And you can see that the runtime is 400 milliseconds, which is definitely not good, but I guess we have a huge recursion, and this is the correct answer, which is a good thing. And let's see what the second part is, and I'm feeling already weird about this. After reviewing the available paths, you realize that you might have time to visit a single small cave twice. Okay, a single small cave twice. Specifically, big caves can be visited any number of times. A single small cave can be visited at most once, and the remaining small caves can be visited at most twice, at most once. However, the cave's name start and end can only be visited exactly one each. Once you leave the start cave, you may not return to it. Once you reach the end cave, your path must end immediately. Okay. This is kinda bad. I'm gonna rename this getPaths1. And actually I will refactor this to a getCaves method. And I think you can assume what the code of part 2 will be. GetCaves, getPaths2, and that's all we have. So we just need to implement this getPaths2 method. Ouchie! Just a second, we didn't even need the next node. So we get to have a bonus, so to say. We can visit one small cave twice, which means that we can have something like this. If we're using the bonus, then it's false. If we're not using the bonus, then it's true. So what we can do here is actually have this. If the bonus is already used, then we have to do this. Else, we have two options. But we don't have to use the bonus. Oh, this is getPath too. I can definitely wrap this into a function. But let's not do that. Yeah, that was my dog trying to help me with a bit with this tricky recursion. So we need to branch it a bit more. So again, if we don't have a if we have a big node, we can just run the regular code, get all the paths. If we already use the bonus, sure we cannot refactor this? No. Sure we can. Because I want to use that piece of code multiple times. And you know what? I will keep these same parameters for process as well. Are we using start node in process? Not really. Are we using nexts? Do we need to do that? Now I'm just spitballing here. So, if we start with an already used bonus, that means that we cannot use any small cave twice, and that devolves to the part 1. Otherwise, here, if we haven't used the bonus, we will need to say this is the sum of use bonus now plus don't use bonus now. And then we delete that. Okay, we definitely don't need this. And we already have this situation that if we are moving on to the end, we are just finishing up. And let's actually try to extract this into another submethod and see what we are actually missing. We are missing the next caves, which are actually the caves. So we're just missing the nexts, and these are those. Yep. Next case, start, end, true. Nope. Yep. Except we will not have a start node, because in the next case the start node is missing. So this is a node actually that used to be here. And we can move this here, so then we don't need this. And we need start.name here as well. Let's have this explicit so we don't get any problems. Yeah, now it's compile error. So instead of that, we're pushing it the start node and true, because use bonus is true. Otherwise will be yep, as we're not deleting the start node. And then we delete the start node anyway and call this with a false. Else, this is the simplest case. When we have a big one, just push everything through. So this is the case that if we use the bonus now, that means that we are not deleting anything, we are not doing anything. We are just calling process2 as this would have been a large node, but the bonus is already used. So the next time that we're gonna call, we're gonna remove this node from the valid nodes. I have no idea whether this will work. Let's just move get caves somewhere here and let's see if this actually makes any kind of sense. I have no idea. One way to find out. Let's go back to the small example with a list of 36 paths. Well, we found 86 of them. That's good. That's different. The good thing is that this thing actually found something and actually finished running. Since there are 86, we might need to do some analysis to see what are the ones that we found but should not have been found. Well, we definitely found start, B, end, and that's it. But we found quite a lot more. Oh, even on the first one I see the problem. We started from start, then we went to 8, then we returned to start. And we need to explicitly exclude. As I already mentioned, that we are excluding that part for the end. So once we get to end, we're done. But once we start from start, we should be start. Well, just don't do that. So if the next node is the end, finish moving. If the next node is the start, ignore that part. Let's go to the terminal and detach from this so that we can run a proper setting, and let's see how many values we get now. We got 59, which is still different from 36, but it is a bit on the better side. So let's see where we've gone wrong. And let's take these in a separate. Actually, let's mangle the output a bit so that we can do it in a better way. We can compare them in a better way. So paths.map join not with a dash but with a comma. Yep, we got all these. And let's see. These are all the valid ones. Is it possible that we have duplicates? Let's see if we are getting this one. Yep. Our fifth path is over there, our 33rd path is over there, and our 41st path is over there. So what I'm gonna do is something kinda silly. That one, and we need another one. We're gonna distinct them. We can add a bunch of complicated checks whether the path has already been done, whether we are redoing something that we already have, but this one actually went relatively smooth and we got 36. And let's see, the slightly larger example should give me should give me 103. Yep. The even larger example should give me 3509. And that is gonna give me 3509, and our actual input will give us hopefully it won't give us an error or a timeout or something like that, but we can wait around for it. Let's wait for a second or so. Oh, it's 12 seconds and it gave us 89,000. All those copying things back and forth. So let's see if this is the correct. Yes, this is the correct answer, and we have done today's task successfully. But let's run it one more time to see how much time it actually takes without debugging, without anything. So the first task that takes 300 milliseconds and the second part takes 13,000 milliseconds. And the code is correct, but I'm not quite happy with the performance, because let's include this into our run all solution that runs all the tasks that we have done so far. 12. Yeah, we got to part 12 and now we're gonna wait a bit. "96% of our running time was taken up by task 12, and most of that was done by part 2. So yes, I'm not happy with this performance, but I am quite happy that we managed to get a solution. So I will stop this video right about now, in the sense that we got a solution and I will have to do some thinking and analysis. I will also do an analysis, because the first thing of performance optimization is that the first 3 rules basically is that you need to measure, measure, measure. If you don't measure what you are doing, you might be optimizing the wrong thing. I have some senses. I think that this part might be slow. But until I measure it, I have no idea. Maybe that's the actual fast part. And this part is slow. And I could spend hours or even days optimizing this specific call, and then determine that I've optimized it. I've made this call to be 200,000 times faster, but that was only 0.5% of the total runtime. So first you need to measure where the problem actually is. Maybe we have too many function calls. Possible. We might benefit then from changing it from a recursive to an iterative object, to using some kind of queues and things like that. Maybe we're copying, maybe we're using too much memory. I don't know at this moment. I have some quite good ideas and some of them will pan out, but I need to measure them. And we will do that most likely in a separate video. For now, thanks for watching. See you tomorrow.